When the United States officially switched to color television, it marked the end of a 30-year engineering struggle. The moment that dial flicked from off to on, the country moved into a new technical era that had been decades in the making. While the ability to capture color light existed as early as the 1930s, releasing it posed a massive economic risk. By the time the technology was ready for the public, over 5 million black and white TVs were already in American living rooms. Any new broadcast format that rendered these expensive sets obsolete would have failed instantly. Added to this was a strict regulatory limit. Because the airwaves were already crowded with military, shipping, and aviation signals, the FCC mandated that every TV channel fit into a narrow bandwidth of exactly 6 megahertz. This diagram shows the technical conflict. A standard 6 MHz box was built to hold one grayscale signal, but a color image requires 3 separate data streams for red, green, and blue. Engineers had to find a way to pack all that extra information into the same narrow space without interfering with the signals older TVs relied on. Solving this required rebuilding the physical mechanics of how cameras captured light and rewriting the mathematical code of how that light traveled through the air. At its core, television works by breaking an image down. Instead of broadcasting a whole photograph at once, it converts light into individual lines of electrical signals, transmits them, and then repaints those lines sequentially on a screen. This 1925 machine by Scottish inventor John Logie Baird was the first to prove this concept. It used a mechanical spinning disc to scan a subject and turn light into electricity. Baird's system was limited by the speed of its moving parts. With only 30 lines of resolution and a frame rate of 5 per second, the resulting image was both blurry and choppy. This animation illustrates how Baird attempted to introduce color. He split the scanning disk into 3 sections using red, green, and blue filters. The camera recorded the light levels for each color, flashing them onto the screen fast enough that the human brain blurred them into a single image. The experiment proved color transmission was possible, but physical discs could never spin fast enough to produce a high-definition image. For television to evolve, it had to move away from mechanical parts and towards the speed of electrons. The transition to electronic television centered on the cathode ray tube and the iconoscope. Developed by Vladimir Zworykin in 1933, the iconoscope replaced mechanical scanning with a beam of electrons that could paint light across a screen at thousands of miles per hour. Adapting this for color initially required 3 separate cameras and 3 separate display tubes for red, green, and blue. This made the early equipment massive, prohibitively expensive, and fundamentally incompatible with standard black and white broadcasts. RCA condensed this into a single tube. 3 electron guns fired at microscopic red, green, and blue phosphor dots. A metal shadow mask just behind the screen ensured each beam strictly hit its corresponding color dot, guaranteeing accuracy. While the shadow mask solved the hardware problem, it didn't solve the bandwidth crisis. Engineers still had to fit that data into the FCC's 6 MHz limit. Sending raw red, green, and blue signals simultaneously would have tripled the amount of radio space required, making it impossible to broadcast. It also would have created a signal that old black and white TVs couldn't process. They combined the color signals into a grayscale luma wave. The remaining color was encoded into I and Q waves, shifted out of phase to create chrominance. Layering this chrominance wave directly on top of the luma signal fit everything inside the 6 MHz limit. Black and white sets simply filtered this frequency out and played the image as normal. Color TVs, however, locked on to the 3.57 MHz signal, reversed the math to extract the red, green, and blue values, and fed that data to the electron guns. This encoding method allowed the color information of the future to hide inside the broadcast standards of the past. This mathematical approach became the NTSC standard, serving as the foundation for American broadcasting for over 60 years. It allowed for a gradual market transition. Because color broadcasts didn't break existing sets, the 2 formats coexisted in stores and living rooms until color sales finally overtook black and white in the 1970s. Faced with rigid government regulations and a massive, inflexible consumer market, engineers integrated the physics of light and the math of radio waves into the existing broadcasting infrastructure. Mapping high-density color data onto the specific technical constraints of the 1940s allowed the new format to scale without rendering 5 million living rooms obsolete. It remains one of the most successful examples of engineering for backward compatibility.